loud, so we should be recording. I'm happy to introduce Lucas Mason-Brown from Oxford. He's going to talk to us about what is a unipotent representation.
Thank you, and thank you for the invitation to speak. My talk today is about infinite dimensional representations of real and complex reductive Lie groups. And the fundamental problem in the subject goes back at least 100 years. It's called the problem of the unitary dual. And the problem is to classify, given an arbitrary group G, the set of equivalence classes of irreducible unitary representations. And as I said, this problem remains unsolved in general. I'll say a bit more about the status of this problem in a few slides. But one of the important and influential ideas goes back to Arthur and Vogan and others. The idea is that the classification of irreducible unitary representations should reduce to the classification of a small finite subset of representations called unipotent representations. And the unitary dual should be, these unipotent representations should function as building blocks in some sense for the unitary dual. And their classification in turn should be related to nilpotent coadjoint orbits. So this has been a kind of guiding principle for the past, I don't know, 40 years. One of the big problems with this idea is that there is no completely satisfying definition of unipotent representations. So in this talk, I'm going to provide a geometric definition of unipotent representations for a complex reductive algebraic group. I'm going to describe some of the key properties of these representations. Most importantly, their unitarity, their restrictions to a maximal compact subgroup. I'm going to describe their annihilators. I'm going to try to relate this set of representations to the representations considered by Arthur called special unipotent representations. It turns out the set of representations I'm going to define is a generalization of Arthur's definition. And then I'm going to sketch a geometric classification of the representations in question. But before I go any further, I just want to mention that this is almost all, except for maybe a few comments at the end, joint work with Ivan Lusztig and his graduate student, Mitya Matvievsky. But before I explain our definition, I want to start with a kind of motivating analogy. So the idea of unipotent representations has its origins in the representation theory of finite Chevalley groups, where unipotent representations were first introduced by Deligne and Lusztig. So I want to say a few words about this theory and kind of what it says about the case of real and complex groups. So to begin with, let FQ be a finite field with Q elements, and let G be a connected reductive algebra over FQ. Consider the finite group of FQ rational points. And can I just ask? I think someone has their microphone. Oh, maybe that's the room. Anyway, so in this world, the problem is to classify the irreducible finite dimensional representations of GFQ, and this problem was solved more or less completely by Lusztig in the early 1980s. So let me try to briefly summarize the structure of his solution. So the first ingredient is a construction of representations. If you have a Frobenius stable maximal torus, T and G, and a character theta of its FQ rational points, Deligne and Lusztig define a virtual finite dimensional representation denoted RT theta of GFQ, which has a geometric construction via the L-adic cohomology of a certain algebraic subvariety of the flag variety called the Deligne-Lusztig variety. And one of their big theorems is that every irreducible representation of this finite group appears as a constituent in some RT theta. And furthermore, for generic choices of T and theta, this representation is irreducible. And in the same paper, they give a definition of a unipotent representation. For them, a unipotent representation is an irreducible constituent in RT1 for some rational torus T. An important observation here is that there are only finitely many conjugacy classes of rational tori in G, and therefore only finitely many unipotent representations, since this RT theta only depends on the conjugacy class of the pair T theta. And Lusztig shows, Lusztig shows in a subsequent paper that the classification of all finite dimensional representations of GFQ reduces in some sense to the classification of this small finite set of unipotent representations. Lusztig also gives a classification of these unipotent representations in terms of some parameters related to the complex Langland's dual group. So for this discussion, let G be the complex reductive algebraic group associated with G, and let G check be the Langland's dual group. There is a notion of a special nilpotent orbit, which I'll explain in a moment. And if you have a special nilpotent orbit, you can consider the finite G equivariant, the finite equivariant fundamental group of this orbit. And this finite group admits a canonically defined quotient group called Lusztig's quotient, usually denoted A bar. And Lusztig's result is that the set of unipotent representations is parameterized by triples, consisting of a special nilpotent orbit for the complex dual group, O check, and a conjugacy class in Lusztig's quotient, and finally an irreducible representation of the centralizer of some element of that conjugacy class. And a particular consequence of this result is that the classification of unipotent representations is independent of the characteristic. So just to summarize what we've seen so far, in the world of finite Chevalley groups, there's a finite set of irreducible representations called unipotent representations with the following two properties. The set of unipotent representations is parameterized by some data related to nilpotent coadjoint orbits for the complex dual group. And the classification of all representations reduces by some kind of procedure analogous to the Jordan decomposition of matrices to the classification of this small finite set. So this is more or less the kind of story that we want to emulate in the case in the world of real and complex reductive Lie groups. So let's replace FQ with a field, either R or C, and let's replace GFQ with the K points of G. And instead of considering finite dimensional representations of GFQ, we're going to consider unitary representations of GK. And as I said, in this world, the analogous problem is unsolved. The problem is to determine and to classify in some sense the irreducible unitary representations of GK for arbitrary G. So we know the answer in some special cases. We know the answer for, of course, for compact connected groups, all irreducible unitary representations are finite dimensional and classified by highest weights. For SL2R, the unitary dual was worked out by Bargmann in the 40s. Vogan worked out the unitary dual of the general linear groups over the real and complex numbers in the 1980s. And Dan Barbasch worked out the unitary dual of the complex classical groups later in the 1980s. And the answer is also known in a bunch of low rank examples. And I should mention that we also, although there's no satisfying general answer to this problem, we do have software which can compute the unitarity of a given admissible representation, at least in principle. So as I mentioned at the top, one possible strategy for approaching this problem is to try to imitate Lustig's theory for finite Chevalley groups, which is to say, to find a finite set of irreducible unitary representations of GK, which plays the same role in the unitary representation theory of GK that Lustig's set plays in the finite dimensional representation theory of GFQ. So this set, first of all, should have the following two properties. It should be parameterized by some geometric objects related to nilpotent orbits. And the classification of all unitary representations should reduce in some sense to this finite set. And in his orange book from the 80s, Vogan described some additional expected properties of these mysterious unipotent representations. Their annihilators should be maximal ideals in the universal enveloping algebra. I'll say some more about this later. They should also be completely prime ideals. If you take one of these representations and you restrict it to a maximal compact subgroup, what you get has a very special and constrained form. Roughly speaking, it should look like the global sections of a certain k-equivariant vector bundle. And the infinitesimal characters of these representations should be as small as possible in their translation families. So many of these properties have to do with the fact that unipotent representations, at least intuitively, are very small. Their annihilators are very big, and their infinitesimal characters are very small. And when you restrict them to k, you get something kind of manageable. So this is I'm going to provide a definition of this set in the special case when k equals c. So let me fix some notation. For complex groups, there is a well-known equivalence of categories between the category of admissible representations of G, regarded as a Lie group, and Harish-Chandra bimodules. So let me just remind you of the definition. A Harish-Chandra bimodule is a bimodule for the universal enveloping algebra of G, for which the adjoint action integrates to an algebraic action of the group. So this already is a fairly remarkable equivalence. The left-hand side involves some amount of topology. These representations on the left-hand side are continuous, for example, whereas the right-hand side of this equivalence is purely algebraic. And for that reason, most of what I'm about to say is going to take place on this side of the equivalence. So when I talk about representations or unitary representations of G, I'm really talking about Harish-Chandra bimodules. If you have a Harish-Chandra bimodule, you can consider the left and right annihilators. These are two-sided ideals in the universal enveloping algebra. And if you have any ideal, say I in the universal enveloping algebra, then it inherits a filtration from the natural filtration on UG, and the associated graded is identified with an ideal in the algebra of functions on G star by means of the Poincare-Birkhoff-Witt isomorphism. And so but by definition, the associated variety of I is just the variety associated to this ideal, which is a closed conical subset of G star. And if the ideal I is primitive, or more generally, if it intersects the center of the universal enveloping algebra in an ideal of finite codimension, then the associated variety, in fact, lives in the nilpotent cone. And if this bimodule in question is Harishchandra, it's easy to see that the left and right annihilators have the same associated variety, which is denoted V of M. And an additional non-trivial fact is that if M is irreducible, then in fact this variety is irreducible. That is, it's the closure of a single coadjoint orbit. So in a paper from 1985, Barbasch and Vogan define a very important class of representations called special unipotent representations. And their definition was inspired by some very interesting ideas of Arthur. So I'm going to take a moment to summarize the definition. The first ingredient is this order reversing map called Barbasch-Vogan duality from nilpotent orbits for the dual group to nilpotent orbits for the group. For example, if G is GLN, then G check is PGLN, and both the domain and codomain are parameterized by partitions of N. And this duality map is just the transpose map on the level of partitions. So this example is somewhat misleading in the sense that D in this case is a bijection. Usually D will be neither injective nor surjective. The G orbits in the image of this map are called special nilpotent orbits. And in all types other than type A, there are non-special orbits. So if we have a dual orbit O check in mind, we can define a very important infinitesimal character for G using the Jacobson-Morozov theorem. We first pick some nilpotent element E check in O check, and we form an SL2 triple, E check, F check, H check, with H check semi-simple. And we consider 1/2 of H check, which defines a W orbit in H check, which is canonically identified with the dual of H, the Cartan subalgebra of G. And this Weyl orbit gives us an infinitesimal character by means of the Harishchandra isomorphism. And if you have any infinitesimal character, there's always a unique maximal primitive ideal in the universal enveloping algebra with that given infinitesimal character. And we'll denote the ideal in question by J 1/2 H check. And an important fact is that the associated variety of this ideal is just the closure of the Barbasch-Vogan dual of O check. And in fact, this is perhaps better viewed as a definition than a proposition. This is more or less how Barbasch and Vogan define their duality map. So for Barbasch and Vogan, the special unipotent ideal attached to O check is the maximal ideal J 1/2 H check. And a special unipotent representation attached to O check is just any irreducible Harishchandra bimodule, which is annihilated on both sides by this particular ideal. And these representations have been very extensively studied, both in the world of complex groups and also their cousins in the world of representations of real reductive groups. And they're known to satisfy lots of nice properties. Their infinitesimal characters are as small as possible. I won't say much more about that. Obviously, their annihilators are maximal by definition. It turns out in all known cases, these representations are unitary. The unit for complex groups, this was for complex classical groups rather, this was established by Barbasch in the late 80s, and then in some exceptional groups by Barbasch and Shibutaru. And remarkably, these representations emit a classification which is at least superficially very similar to Lustig's result. So they prove that the set of special unipotent representations of G attached to some orbit O check is in natural bijection with irreducible representations of the corresponding Lustig quotient group. That's very nice. But it's pretty clear, and it was certainly clear to Barbasch and Vogan, that their definition is incomplete. That it includes only a small fraction of the representations which deserve to be called unipotent. And one of the clearest examples of this fact occurs in the symplectic groups. So there is the minimal orbit for sp2n is known to be non-special. And there's a very important maximal completely prime ideal called the Joseph ideal, which is attached to this orbit. And some very important irreducible unitary representations called the oscillator representations or the metaplectic representations, which are annihilated by this ideal. The problem is that this orbit O, this minimal orbit, is both rigid and non-special. Because it's non-special, these oscillator representations are not special unipotent. And because it's rigid, these oscillator representations can't be obtained by parabolic induction from some representations of a proper Levy subgroup. And yet, philosophically, unipotent representations are supposed to be the building blocks of the unitary dual. So we have to include, we're sort of forced to include by these facts, the oscillator representations as unipotent representations. So in the next few slides, I'm going to propose a natural definition of unipotent representations of G, which includes all of Arthur's representations, but also other representations like the metaplectic representations, which play a privileged role in unitary representation theory, and which sort of capture some of the spirit of Lustig's theory for finite Chevalley groups. So in the scheme I'm going to propose, unipotent representations will be parameterized not by orbits, but by nilpotent covers. So a nilpotent cover is a triple consisting of a nilpotent orbit and a homogeneous space, O tilde for G, and a finite G equivariant map. So obviously these things can be classified fairly easily. If you pick a point E in the orbit and a point X lying over E, then the equivariant fundamental group of O is identified with the component group of the centralizer of E, and the equivariant fundamental group of O tilde is a subgroup of the fundamental group of O, which is identified with the component group of the stabilizer of X. And this subgroup is, of course, it depends on your choices of E and X, but it's well defined up to conjugation within the fundamental group of O. So this sets up an order reversing correspondence between nilpotent covers of a given orbit O and subgroups of its equivariant fundamental group up to conjugacy. So just to give, a slightly non-trivial example, if the group is G2 and the orbit is the subregular orbit, denoted G2A1, then the fundamental group of O is S3. This is one of the bigger fundamental groups you'll encounter. And S3 has up to conjugation 4 subgroups. The trivial subgroup, there's a conjugacy class of subgroups isomorphic to Z2, isomorphic to Z3, and then S3 itself. And the trivial subgroup corresponds to the universal cover of O, and S3 corresponds to the orbit O itself, and Z2 and Z3 correspond to threefold and twofold covers, respectively. So an important fact about these covers is that they have natural G-equivariant symplectic forms. You just take the symplectic form on the nilpotent orbit and you pull it back along the covering map. And the symplectic form, if you look at the ring of functions on the cover, this symplectic form induces a graded Poisson bracket on the ring of functions. And so it makes sense to talk about filtered quantizations of these coverings, or rather their affinizations. So for us, a quantization of O tilde is a pair consisting of a filtered algebra A with such that the commutator reduces degree, and an isomorphism of graded Poisson algebras, where the Poisson structure on A is defined using the commutator. Sorry, the Poisson structure on GER A is defined using the commutator on A. We define, A plus A less than or equal to M, bracket B plus, this is defined to be A commutator B plus A less than or equal to M plus N minus 1. So in general, it's very difficult, for general Poisson varieties, there is no nice classification of filtered quantizations. But for nilpotent covers and more generally conical symplectic singularities, there is a very nice theory due mostly to Ivan Losztig. In the case of covers, the theory says the following. To every nilpotent cover, there is a Levy subgroup, L in G, and a finite Coxeter group W, which acts on the center of the Lie algebra of L by reflections. And there is a canonical bijection between isomorphism classes of filtered quantizations of O tilde and W orbits on the center of L. So this result was proved for orbits by Ivan Losztig, and then for covers by his student Matwiejewski. And then in our ongoing joint work, we proved that the resulting bijection is canonical, which is not completely clear from the original construction. So let me give just a few examples of this parameterization. If O is the principal orbit, then the Levy in question is the maximal torus, and the Coxeter group in question is the Lie theoretic Weil group for G. And so the conclusion is that quantizations of the nilpotent cone, filtered quantizations of the nilpotent cone, are parameterized by Weil group orbits on T star. And in this case, and pretty much only in this case, the bijection is very easy to describe. If you have a Weil group orbit on T star, lambda, you get an infinitesimal character, chi of lambda, and its kernel generates a two-sided ideal in UG, and you can form this central reduction, which turns out to be a quantization of the ring of functions on N. And the statement is that all quantizations are of this form, and no two such are isomorphic. So for our purposes, the important observation is the following. If O tilde is an equivariant nilpotent cover, there's always a distinguished quantization 0. distinguished quantization corresponding to the point 0 in the center of this levy. And we call this quantization the canonical quantization, and we denote it by A sub 0. And we describe a bunch of properties that this quantization has. It turns out this quantization is the unique even quantization of the ring of functions on O tilde. This filtered algebra has a very large automorphism group. In particular, every Poisson automorphism of O tilde lifts to a filtered algebra automorphism of A0. And in particular, the group action of G on O tilde, which is by Poisson automorphisms, lifts to a group action on C O tilde by filtered algebra automorphisms. And so this is automatically an equivariant quantization of the ring of functions on O tilde. And in fact, more is true. It's a Hamiltonian quantization, which means there is a distinguished filtered algebra homomorphism from UG to A0, which lifts the classical co-moment map, which is the natural one from SG to CO tilde. And so our definition is the following. The unipotent ideal attached to O tilde is the primitive ideal, J O tilde, which is the kernel of this uniquely defined quantum co-moment map. I guess it's not immediately clear from the definition that this is a primitive ideal, but it is. And it also has these ideals have lots of really wonderful properties, but before giving them, I want to just sketch a few examples. So these are two very trivial examples. If the orbit is the zero orbit, then this co-moment map is just the augmentation map, and the unipotent ideal is just the augmentation ideal, which has infinitesimal character rho, which is good because rho is the infinitesimal character of the trivial representation. On the other extreme, if O is the principal nilpotent orbit, then this canonical quantization is the central reduction at infinitesimal character 0, and J of O is just the unique primitive ideal with infinitesimal character 0. So the infinitesimal character. So in the sort of largest possible case, which is the principal orbit, the unipotent ideal has infinitesimal character 0, and in the smallest possible case, it has infinitesimal character rho, and all of the other covers give ideals which are sort of in between. So just to give a slightly less trivial example, if we consider the twofold cover of the principal orbit of SL2, it turns out easy to see that the equivariant fundamental group of the principal orbit here is Z mod 2Z, and so there's a twofold G equivariant cover. And its affinization is just C2, the affine plane, which has a unique quantization, namely the Weil algebra. And the Weil algebra has a natural Z2 action, where Z2 acts by negation on X and partial X. And the Z2 invariance in the Weil algebra is therefore a filtered quantization of N. We saw previously that all filtered quantizations of N are central reductions of UG, and we can figure out exactly the infinitesimal character by constructing an explicit homomorphism, which I've done here, and I won't really explain further. If you do this computation, you find that the unipotent ideal associated to the twofold cover has infinitesimal character rho over 2. So halfway between the principal orbit and the 0 orbit. So here are some very general properties of unipotent ideals. First, not very surprisingly, the associated variety of the unipotent ideal attached to a cover, O tilde, is just the underlying orbit. All of these ideals are completely prime. This property is not so surprising. These quantizations are domains because they quantize, well, they quantize irreducible varieties. And these ideals are defined to be the kernels of maps to these domains from UG. So that's more or less automatic. What's not automatic is that they're maximal ideals in the universal enveloping algebra. And furthermore, if these ideals are of multiplicity 1 along their associated varieties, if and only if the cover is Galois. So I'm going to give a bunch of examples of unipotent ideals. Here on this plot, I've indicated the 4 special unipotent ideals for the group SP4. So there are 4 of them because, as I mentioned, special unipotent ideals are parameterized by orbits for the dual group. And in this case, the dual group SO5 has 4 orbits. And these unipotent ideals are labeled by their associated variety. So there's a unipotent ideal with infinitesimal character rho, which is attached to the 0 orbit, and there's a unipotent ideal with infinitesimal character 0, which is attached to the principal orbit, and then there are these 2 ideals attached to the subregular orbit. And there's of course there is a 4th ideal. There's a 4th nilpotent orbit for SP4, which is the minimal orbit, and this orbit doesn't have an ideal attached to it because it's not special. So in our scheme, we distinguish these 2 special unipotent ideals by attaching one of them to a 2-fold cover. We attach an additional ideal to the 2-fold cover of the principal, and then we attach a unipotent ideal to the minimal orbit of SP4, which turns out to be the Joseph ideal. So here's some data. These are the, this is a list of all of the infinitesimal characters of unipotent ideals attached to orbits and covers for SP8. So again, you can see attached to the principal orbit. By the way, I've indicated orbits using partitions of 8, certain partitions of 8. And the degree of the covering is indicated with a little subscript. So this first guy is the principal orbit, and this last one is the 0 orbit. The second one, for example, is the 2-fold cover of the principal. And calculating these infinitesimal characters actually requires a huge amount of work and geometry, which I won't get into in this particular talk. I just want to highlight a few things about these infinitesimal characters. First of all of the special unipotent ideals appear on this list, and they're all highlighted in blue, but lots of others as well. You can see here attached to the minimal orbit is the infinitesimal character of the Joseph ideal. You can also see that some non-isomorphic covers give rise to the same unipotent ideal. So you see that here, for example, and also here. And that's not an accident. We describe exactly when this happens. So we define as an equivalence relation on the set of nilpotent covers. Namely, 2 covers are equivalent if their affinizations have the same codimension 2 singularities. I'm missing a symbol here. See. So this defines an equivalence class on the set of all nilpotent covers. And we prove that the set of unipotent ideals is precisely parameterized by equivalence classes of covers. So to give an example, for SL2, you have these 3 nilpotent covers. You have the 0 orbit, you have the principal orbit, and then you have its 2-fold cover, O tilde. And the infinitesimal characters are 1, which is rho, and 0, and then rho over 2. So they're all different. And indeed, the affinization of O is the nilpotent cone, which is singular in codimension 2, and the affinization of O tilde is C2, which is smooth. On the other hand, if you take a minimal orbit for any group, which let's say has dimension bigger than 2, then there are no orbits in the boundary. There are no codimension 2 orbits in the boundary, and therefore no codimension 2 singularities in the affinization. And consequently, no codimension 2 singularities in the affinization of any cover. So it follows from our definition that all of the covers of the minimal orbit are equivalent, and hence there's only one unipotent ideal there, which turns out to be the Joseph ideal. So one interesting question is to describe the relationship between our ideals, which are parameterized by nilpotent covers on the group side, and the Arthur Barbasch-Vogan ideals, which are parameterized by nilpotent orbits on the dual side. And it turns out that the key to unlocking this relationship is a certain refinement of Barbasch-Vogan duality, which is as follows. There is an injective map from orbits, nilpotent orbits for the dual group to equivalence classes of covers for the group. And this map has the property that the dual of O check is a set of covers over the Barbasch-Vogan dual of O check. So we have this Barbasch-Vogan map, and this triangle commutes. And secondly, the infinitesimal character, the unipotent infinitesimal character associated to the dual cover of O check is exactly this Barbasch-Vogan 1/2 H check. So what this tells us is that, since all of the ideals are maximal, is that all special unipotent ideals, in the sense of Barbasch and Vogan, are unipotent in our sense. And it tells us exactly which covers they quantize. So for us, unipotent representation is just an irreducible Harish-Chandra bimodule, which is annihilated on both sides by one of these very special ideals. And we prove that, at least in the case of linear classical groups, all of these representations are unitary. By the way, this implies that all of the special unipotent representations are unitary in complex classical types by the previous result. We also show that we also prove a conjecture of Vogan regarding the G types of unipotent bimodules. We show that if V is a unipotent bimodule attached to O tilde, then there is a distinguished good filtration on V and an isomorphism of G representations between V and the global sections of Gur-V, which is a G equivariant coherent sheaf over the orbit O. And this, of course, is just, as a G representation, this is just, some induced, you pick E and O, and you look at the centralizer of E, and you induce the sort of the geometric fiber of this vector bundle from GE up to G. So this shows that unipotent representations as G representations have this very, very pleasing form, as conjectured by Vogan. And we also give a geometric classification of the representations in question. So the way this works is you first show that every equivalence class of covers has a unique maximal element. And since all of the covers in an equivalence class, correspond to the same ideal, you can harmlessly replace O tilde with this maximal cover. And we consider, instead of Lusztig's quotient, which is what appears in the Barbasch-Vogan result, we consider this finite Galois group. And our result is that there is a natural bijection between unipotent representations of G attached to O tilde and irreducible representations of this Galois group. And I should mention that a sort of, a bonus feature of this result is that it gives an alternative geometric characterization of Lusztig's quotient. Namely, Lusztig's quotient, Lusztig's quotient can be interpreted as a Galois group for a certain dual cover. So I wanted to say a few words about real groups, but I think in the interest of time, I'm going to stop and see if there are questions.
Let's thank the speaker.
So I guess the next step is to show that you can get the other representations out of the unipotent representations in some way.
Yeah, and this follows from, at least in complex classical groups, this follows from Barbasch's work. It's a sort of tedious check. We haven't checked in general that these representations have that property.
And is that the sort of the parallel to Lusztig's picture? I mean, is it a similar kind of construction in some way? In some sense?
I mean, in the case of complex groups, it's the relevant induction is unitary induction and the formation of complementary series. You have these two tools for producing representations of G from representations of some levy. You can either unitarily induce, or you can do a complementary series construction which preserves unitarity. And the hope is that all unitary representations of G can be obtained from unipotent representations of a suitable levy by performing these two operations kind of in sequence. That's the hope. But proving that is more or less equivalent to solving the problem of the unitary dual, which we didn't do in this paper. But the hope, which is borne out in some examples, is that these unipotent representations do kind of form the building blocks.
Mm-hmm. Okay, very good.
Yeah.
And how far are you from getting an answer for real groups?
Yeah, I wanted to say something about that. I think it's quite a bit more difficult. I think there is a kind of naive extension of this definition to real groups, right? A representation of a real group is the same thing basically as a Harishchandra module, right? A GK module where K is a maximal compact subgroup. And you could define a unipotent representation to be an irreducible GK module which is annihilated by one of these ideals. But you see already for SL2R that this is not the right definition because it gives some non-unitary representations. So for example, if you consider the twofold cover of the principal orbit, the ideal there has infinitesimal character 1/2, and there are two representations of SL2R with infinitesimal character 1/2. There is this spherical representation, then there's a non-spherical representation. And the spherical representation is unitary, it's a complementary series representation, but the non-spherical one is not unitary. However, right, it's not unitary. So you have to add, the naive definition is not restrictive enough. You have to impose some additional conditions. And my belief is that if you replace G with a suitable covering group, that the unitarity is guaranteed. But this is not something I've really figured out. It's an extremely interesting question, though.
Okay, good.
Any other questions for the speakers? Okay, let's thank Lucas again.
Thanks,